I want to take you on a journey through the history of computing, how machines have evolved over the last 50 years, the role of instruction set architecture, the rise of open hardware, the impact of machine learning, and even the meaning of technological progress in our lives. My goal is to help you not only understand where we've been, but also where computing might be heading. 50 years ago, computers filled entire rooms. They were expensive, fragile, and reserved for governments or research institutions. A graduate student might have been lucky to get a few hours of computing time per week, running programs by feeding punched cards into a machine. Today, the power of those room-sized systems fits into the palm of your hand. The real breakthrough was the invention of the microprocessor. The idea that the processor, memory, control unit, and arithmetic unit could all live on a tiny silicon chip. The first commercially available microprocessor, the Intel 4004, came out in 1971 with just over 2,000 transistors. Compare that with modern processors, which contain tens of billions. That's not just evolution, that's revolution. Think about this. A computer in 1975 might have cost hundreds of thousands of dollars and filled racks of equipment. Now, your smartphone, powered by billions of transistors, can execute instructions a million times faster and costs a fraction of the price. In fact, there are more microprocessors in the world than people. Some estimates suggest more than 10 per person. They're everywhere, in your car, your watch, your washing machine, even inside medical devices. We live in a world where computation is as common as electricity, something woven invisibly into daily life. At its heart, every computer, whether it's an IBM mainframe in 1960, a Cray supercomputer in the 1980s, or an iPhone today, shares the same five components: input and output, the way we talk to machines and they talk back; memory, which stores instructions and data; the arithmetic unit, the body doing calculations; and the control unit, the brain coordinating everything. When we say microprocessor, we are really talking about putting the arithmetic unit and control unit onto a single chip. And what's fascinating is that despite decades of progress, the core ideas have hardly changed. It's a bit like the automobile. The engines today are light years ahead of the first Ford Model T, but the basic principles of four wheels, an engine, and a steering wheel have endured. Computers are complicated, so complicated that the only way humans have managed to design and use them is through layers of abstraction. You can think of it like an onion. At the very bottom are transistors, tiny switches flipping billions of times per second. Above that, we have logic gates, instruction sets, compilers, operating systems, libraries, and applications. Each layer hides the messy details of the layer beneath it. Here's the beauty. A student starting with Python can peel back these layers step by step, moving down to C, then to assembly, and eventually to transistors themselves. Every layer is connected, but we are free to zoom in or zoom out, depending on our curiosity. Without abstraction, computers would be unusable. With abstraction, we've been able to build everything from video games to weather prediction systems to space exploration missions. One of the great debates in computer science was RISC versus CISC. CISC, or complex instruction set computing, believed that processors should offer powerful, complicated instructions. The idea was that these instructions would make software development easier. RISC, or reduced instruction set. Computing took the opposite view. What if, instead of fancy operations, we gave processors a smaller, simpler vocabulary, things like add, subtract, load, store, but made them blazingly fast? Critics said RISC was a step backward, almost like returning to the Stone Age of computing. But here's the twist. When benchmarks were run, RISC often won. Why? Because simpler instructions could be executed more quickly, and compilers, automated translators of code, could handle generating the extra instructions. This approach turned out to be more efficient in practice. The result was that RISC architectures became the foundation for ARM, which powers virtually every smartphone on the planet. In other words, the phone in your pocket is built on the radical idea that simpler is better. Fast forward to 2010. At Berkeley, a group of researchers revisited these ideas and launched RISC-V, an open instruction set. Why does this matter? For decades, instruction sets like Intel's x86 and ARM were proprietary, guarded like treasure. Companies paid millions in licensing fees just to use them. But a RISC-V is free and open. That means anyone, students, startups, researchers, can design processors without paying those fees. It's a bit like Linux for hardware. Open, collaborative, and already spreading quickly across academia, embedded systems, and even large companies. In just a decade, RISC-V has gone from a classroom project to a movement shaping the global tech industry. Imagine a world where hardware design becomes as democratized as software development. That's the promise of RISC-V. 10 years from now, it could very well be the dominant global standard. Let's shift from processors to storage. Back in 1988, Patterson and his colleagues proposed RAID, Redundant Array of Inexpensive Disks. At the time, large, reliable disks were extraordinarily expensive. The problem was reliability. If you used one giant disk, a single failure meant disaster. But what if you used dozens of smaller, cheaper disks and added redundancy? That way, even if one failed, you wouldn't lose your data. At first, people laughed at the idea. Why would anyone trust a pile of cheap disks? But the insight was that cheap plus smart could outperform expensive and fragile. It was a simple idea. Cheap hardware plus smart redundancy, but it transformed storage systems. Today, whether you use Google Drive, Dropbox, or iCloud, RAID principles are at work behind the scenes to keep your data safe. In fact, RAID wasn't just an engineering breakthrough, it was a philosophy. Never trust a single point of failure, because eventually it will fail. For decades, computing followed Moore's law. The number of transistors on a chip doubled every 2 years. This relentless march gave us faster, cheaper, smaller machines. The world came to rely on this rhythm like the ticking of a metronome. Every couple of years, you could expect computers to double in performance for the same price. But here's the sobering truth: Moore's law is slowing. Chips no longer double in speed or density every 18 months. Clock speeds have plateaued. Heat has become a bottleneck, and the physics of silicon are reaching their limits. That's why your laptop today isn't dramatically faster than the one you bought 5 years ago. The era of free performance improvements is ending. So, what's next? The answer is accelerators, specialized hardware for specific tasks. And the most important of these is for machine learning. Machine learning has transformed how we use computers. Instead of programming rules by hand, we let algorithms learn from data. Whether it's voice recognition, image classification, or language translation, Machine learning thrives on a single mathematical operation, matrix multiplication. That's why companies like Google developed TPUs, tensor processing units, and why GPUs have become so central. These chips accelerate the one operation that underpins modern AI. The irony is that in trying to build domain specific hardware, we may have stumbled into something broadly general. Machine learning isn't just one domain, it's spreading everywhere, from healthcare to finance to robotics. That's why this decade feels like a new golden age of computer architecture. Think about your daily life. Every time you unlock your phone with your face, an AI model trained on millions of images is at work. When you ask a smart speaker to play music, it's parsing your voice using neural networks. When Netflix recommends a show, when your car warns you to brake, when doctors analyze x rays for signs of disease, all of these rely on specialized hardware built to make machine learning practical at scale. 50 years ago, computing was about numbers. Today, it's about patterns, predictions, and intelligence. Beyond technology, Patterson emphasizes something deeply human: teaching. Explaining concepts to students forces you to confront the why behind ideas. Just like Richard Feynman argued, teaching clarifies thinking. It's not enough to understand something yourself. You need to explain it simply, clearly, and convincingly. That's how ideas spread and endure. He also credits wrestling for shaping his resilience. Wrestling taught him confidence, teamwork, and the courage to stand his ground, whether in sports or in academic debates over risk versus CISC. It's a reminder that life lessons often come from unexpected places. In fact, you could say that innovation requires a kind of intellectual wrestling, grappling with old assumptions, struggling with resistance, and emerging with something stronger. So, what does all this mean for us? True impact comes from ideas that last, from teaching others, from building systems that outlive you. For Patterson, pride comes not just from awards but from mentoring students, contributing to open knowledge and building technologies like RISC and RAID that continue to shape our digital world decades later. It's a lesson for all of us. Progress isn't only about faster chips or bigger storage. It's about building a foundation for future generations. Computers have changed dramatically in 50 years, yet the core remains the same. Simple instructions executed billions of times per second. The abstractions we've built, from instruction sets to open source ecosystems, continue to shape the landscape. As Moore's law slows, machine learning and accelerators open a new frontier. But ultimately, the meaning of technological progress is measured not just in performance, but in the people we teach, the teams we build, and the lasting contributions we leave behind.